Just for fun, let's talk some more about the Fibonacci numbers. So we talked about Fibonacci numbers when we were talking about recursively defined sequences. So of course we know F0, I'm going to say is 1, F1 is 1, and then Fn is Fn minus 1 plus Fn minus 2 for all n greater than 1. Right? So if you actually wanted to write a computer program that would compute the nth Fibonacci number, you could say something like this. So stating that I'm defining a function, here's the name of the function, here's the argument that the function will take. I'm going to say if n, let's say probably double equals or something, 1, I want to start with 0. I'm going to do my base cases and the recursive case. Let me say return 1, else if n double equals 1, return 1, else skip a line. I'm very rusty with the pseudocode. Turn Fn minus 1 plus Fn minus 2. So you can run this program, and it, assuming you correct the syntax, my syntax is not going to be correct, but assuming you put this in the correct syntax, this program will run, but it will take a long time. And I'll post a working version of this so that you can run it, or you can do your own. Probably it's very, very easy. You can see that if you ask it to tell you the 40th Fibonacci number, probably you won't be patient enough to wait for it to finish. It's because this takes exponential growth. This takes, so we talked before about Tn, which is what we call the worst case running time. How many computations is this program going to have to do to calculate the nth Fibonacci number? So, well, let's see. Why is this a stupid algorithm? So this is perfectly correct, but why is it a bad algorithm? In the theoretical aspect of things, this is not so bad because it does the right job. But in a practical sense, this is very bad. It's because, well, if I think about this and I ask this to compute the 10th Fibonacci number, then my computer is going to run through and say, well, I'm not in this case, I'm not in this case, I'm here, so I need to return this thing, so it means I need to compute the 9th Fibonacci number. So my computer is going to go over here and try to compute the 9th Fibonacci number. And in order to do that, my computer is going to go back up here and it's going to read through this again, and it's going to say, oh, I need to do the 8th Fibonacci number. And then it's going to keep going, and it's going to get all the way down to the bottom until it gets down to fib 2 equals fib 1 and fib 0, and it doesn't need to do any more recursion then. It's going to get to fib 2, and then it's going to feed all those answers back up. Okay? And then it's going to get here, and it's going to go, okay, I computed this fib 8, and now in order to finish fib 9, I need to go over here and do fib 7. Okay? But in order to do fib 7, it's going to have to do fib 6. And of course, you and I know that this program has already computed the 7th Fibonacci number. It did it over here. And now it's going to have to do it again. Right? So my computer doesn't know that it's already done that. You're not telling it to save the information after it computes this, right? And the computer won't know to save it itself. So this program is recomputing many of these numbers, which is the reason it takes so long. And if you notice, if I look at this tree, right? So they call this a recursion tree. It's gonna more or less giving me some idea of what programs, which calls are going to make which other recursive calls. So here I have the 8th Fibonacci number, and over here I have it again, which means that in order to compute the 10th Fibonacci number, it's going to take more than twice as long as the 8th Fibonacci number. because it has to compute the 8th Fibonacci number here, and then also this other stuff. Right? So to go from, say, fib n to fib n plus 2 is going to take more than twice as long. So this is exponential growth. Okay? Exponential time. So this Tn is, do it the wrong way, greater than or equal to some exponential time. And that's bad. Okay? You can actually see, I think the time is like base some special number. Let's think about some alternatives. What can we do here? Well, there's a thing called dynamic programming. So as I mentioned before, kind of the stupid thing about the program that I had on the previous page is that it's recomputing numbers that are already computed, and it could save a lot of time if it just remembered the answer from the last time it computed it. And so you can tell your computer to do that. This is, so I'm being a little imprecise here, but there's a general method of programming called dynamic programming, where you, if you have a problem that has a certain, I think you call it perfect problem substructure, which means inside the problem you're doing exactly the same sub-problem many times, which is exactly what we had for Fibonacci numbers. And some other condition about optimality, if I'm optimizing a problem on a subset, then I get the same solution as when I optimize it on the whole thing. And we weren't really optimizing anything in that previous problem, but that does come into play when you're solving other kinds of recursions, like those that occur in the knapsack problem, which are optimization problems, and you have to try to find a maximum overall combinations, and you're trying combinations more and more, and things like that. So dynamic programming is very valuable, very useful programming tool, and roughly the idea is if I can avoid repeatedly solving the same problem by just allocating a little bit of extra memory and then remembering the solution. So here, I think if I wanted to do, say, if n equals 0, return 1, else if n equals 1, return 1, else here I'm going to say p equals 0 and a equals b equals 1. So here, p is going to be a counter, and I'm going to do something and increment the counter, and a and b, those are going to be my initialized Fibonacci numbers. So a is going to be, a and b are going to be two consecutive Fibonacci numbers, and in my mind they started where b is f0 and a is f1, but they're going to update. So here, this is what I meant when I said you allocate a little bit of extra memory. Now I have two variables, a and b, that I didn't have before, and I'm going to save my Fibonacci number results there. Okay. So I'm going to say while p is less than, and I don't remember how many times I need to increment here. I think I want to say n minus 2, or n minus 1, because I'm starting at 0. I need to do n minus 1. I'm going to say a b equals a plus b a. So here, this is updating the values of a and b. A is now getting the a plus b value, and b is getting the b value. Over here I'm just going to make a comment. So in my mind, as I go through this process, b is going to be fp, and a is going to be fp plus 1, and p is starting at 0, so initially b is f0 and a is f1. And then when I update, the new value of a, so this is before update, and then after update, A gets, the new value of A is the previous A plus B value. Well, f of p plus f of p plus 1 is f of p plus 2, and the new B value is the old A value. Okay. So every time this iterates, my A and B values go from these two Fibonacci numbers to the next two. And let's see, when I iterate the correct number of times, A is going to be the one that I want. So for example, if n equals 2, P is going to start at 0, A is going to be F1, this while loop is going to go one time because P is going to start at 0. Of course, I need that step where I actually increment the counter. So P starts at 0, then it goes to 1 after the first time, and then if n equals 2, n minus 1 is 1. After one step, these are equal, so it doesn't do this a second time. And then I just have A is F2, and then I'm done. Let's say return A. And here, I'm actually keeping A and B. Right? I'm not computing, say, so here A and B is where I'm computing the previous Fibonacci numbers, right? So if I want F10, A and B is where I'm computing F1 and 2 and 3 and 4, etc. And I'm storing those results as long as I need them, which is not very long. Right? Here I'm only keeping the last two values of the Fibonacci numbers. And so once I update, so this, notice here I have A and B, and they get replaced. The old value of B gets discarded here. You only need to keep the last two values in order to compute the next one. So I have to allocate just enough memory to save the last two values. This is an example of dynamic programming. It saves a lot of time, and I'll post a working example of this, and you can compare. You can compute a very large Fibonacci number, and it'll finish in just a couple of seconds. So, two other interesting ways to compute Fibonacci numbers. So I'll notice that, so if I have, let's say Fp and Fp minus 1, and I'll put these in a vector. And now I'll notice that if I do 1, 1, 1, 0, just do this matrix multiplication, I get, well, I do 1 times Fp, 1 times Fp minus 1, and then 1 times Fp. So this was my old vector, and this is my new one, but this is P plus 1, and then Fp. If you notice, this is the exact same update that we did in the dynamic programming problem on the previous page. So here this is A and this is B. And then after the update, the A gets replaced with this new value, which is A plus B. And this one gets replaced with the old value of A. Right? So taking A and B values, putting them in a vector and multiplying by this matrix is exactly the same as updating A with A plus B and updating B with A, with the value A. Okay, so, but now what's the point of this? Well, here, this takes two consecutive Fibonacci numbers and gives me the next, kind of shifts by 1. What if I wanted to shift by 2? I just multiply by this matrix again. What if I wanted to shift by 3? I just multiply by the matrix a third time. So, if I start with, say, F1, F0, and then multiply 1, 1, 1, 0, say P times, I'm going to get F of P plus 1 and then Fp. Right? So every time I multiply by this 1, 1, 1, 0 matrix, it's going to shift. Okay, so if I wanted to shift P times and multiply by the matrix P times, and now, if I just want the pth Fibonacci number, I can take this and multiply by 0, 1. And if I take 0, 1, multiply by Fp plus 1, Fp, I get 0 times Fp plus 1, and 1 times Fp, so I just get Fp. technically it's a 1 by 1 matrix that only has one number in it, but that doesn't really matter. So, if I wanted to compute the pth Fibonacci number, I could compute this matrix and then just look and see what's the number in it. And now I've reduced the problem to this problem. How do I exponentiate this matrix? How do I raise this matrix to this power? Well, you're writing this in a computer, you could get your computer to do it for you. And exponentiation of matrix is not great, but it's not so bad. If I'm going to have A, B, C, D, these are 2 by 2 matrices, E, F, G, H. Right? So I'm going to have A times E, B times G, A times F, B times H. So I'm going to have 8 multiplications here and 4 additions. Right? So 8 multiplications and 4 additions. So we assume each of those takes a constant time. Then raising my matrix to the pth power is going to take time that's linear in p. Okay, so doing 8 multiplications and 4 additions is worse than doing a single multiplication, but it's only worse by a constant factor, and if things are very large, those constant factors tend not to matter, and you'll see a lot more of that when you do asymptotic notation and things like that, which we don't cover too much in here. This is a linear time solution to the problem. Now let's see if we can actually do some interesting linear algebra. If you want to know how to find eigenvalues and eigenvectors and diagonalize a matrix, then you need to take linear algebra, which is Math 222. I'm going to use some facts from that. Okay. I'm not really going to explain them, but I'm just going to say something. Cite some facts from linear algebra. So, the previous page we had to raise some matrix to a power, and raising a matrix to a power is computationally for us would be a lot more difficult than raising a single number to a power, because well, I have to do this row times this column and then add the results, and it's not a direct thing. However, let's say P, I don't want to call it P, I want to call it something else. I'm going to call it T. So assume T is 2 by 2 invertible, and I have a matrix A, which is T times, let's say, A00, 0B, T inverse. Okay. So here I have this matrix that has a special form. It's in a matrix times a diagonal matrix. We call this a diagonal matrix because on the main diagonal it has some numbers, and off of the main diagonal it has only zeros. And then I have the inverse of the matrix that's over here. So remember, so note, if I take any diagonal matrix and multiply it by any other diagonal matrix, I just multiply A by C and then B by D. Okay. It's very easy to multiply diagonal matrices because basically there's no interaction between the first row and the second row. There's no interaction between the first column and the second column. Okay. So I can say A00B to the power P, if it's a diagonal matrix, is just this, A to the P, 0, 0, B to the P. So it's very easy to raise a diagonal matrix to a power. A lot easier than it is to raise a matrix like this to a power. And if you want to see, just say raise this one to the 10th power by hand and just find out how much of a pain it is. So it's very easy to raise a diagonal matrix to a power. Just raise the diagonal entries to that power. What about this other matrix A? This is not a diagonal matrix because I have this T and T inverse. But if I do A squared, I get T times the diagonal matrix, A, 0, 0, B, times T inverse. That's A. Now I want to do A squared, so I need another A, 0, 0, B, T inverse. And now, well, matrix multiplication is, it's not commutative, but it is associative, which means I can drop the grouping symbols. Okay. So here I have T times T inverse, which is the identity matrix, because that's the definition of a matrix inverse. The identity matrix is analogous to 1, which means when I multiply by it, it doesn't change anything. So right here I have basically a 1, T, A, 0, 0, B, and then I'm not going to write the 1. Multiplication by this identity matrix doesn't change anything. And now I just have the diagonal matrix by itself. A squared, 0, 0, B squared, T inverse. Okay. So A squared still has the T and T inverse on the outsides, but the diagonal entries have just been squared. Now you can prove this by induction. Okay, so if A, lowercase a, capital A, if capital A equals T, A, 0, 0, B, T inverse, where T is a 2 by 2 invertible matrix, so all the matrices here are 2 by 2. What I'm writing will make sense for not just 2 by 2 matrices, but 2 by 2 is what we care about because that's what we're going to use for Fibonacci numbers. If I want to raise it to the power P, I get T, A to the power P, 0, 0, B to the power P, T inverse. So if I know what T is, and I know what A and B are, then I can raise this matrix A to the power P, and this part I don't actually have to multiply anything by T to go from here to here. The T inverse are just hanging out. So if I want to raise a matrix to a power, it's very convenient to have it written like this. Okay, so let's look back over here, 1, 1, 1, 0. That was our matrix that we wanted to raise to a power if we're going to compute our Fibonacci numbers. So I'm going to compute some eigenvalues and eigenvectors, and we don't know what those are, but just bear with me. So what I'm going to do is look at the determinant. So we did talk about a determinant of 1 minus x, 1, 1, negative x. So on the main diagonal, I subtracted an x, so 1 minus x and 0 minus x. Everything else stayed the same. So this is negative x, 1 minus x, minus 1. I get x squared minus x minus 1. And I want to set this equal to 0 and solve. And I'm going to get two solutions. Okay. So one solution is 1 plus the square root of 5 over 2. You can use a quadratic formula and see that. The other one that I'm going to call, so I'm going to call that one phi. So you probably already have heard of this. It's the golden ratio. The other one I'm going to call phi bar, 1 minus square root of 5 over 2. Okay. And these are eigenvalues. What are eigenvalues? Don't worry about that right now. But now I would like to find some eigenvectors. So what I'm going to do is say, I'm going to take A, and I'm going to do 1 minus phi. So before I had this, I subtracted x, and then I found some x values. I found these two x values. Now I'm actually going to plug those in for x. So I plug in 1 minus phi, 1, 1, negative phi. And I'm going to put some numbers over here, r and s, and I want this to end up being 0. Okay. I want to choose some non-zero r and s, and I want to end up getting 0, and in order to do that, I'm going to say let, well, I'm going to eyeball this and just look at this row. here I'm going to get R minus phi times S, so I'm going to say R equals phi, S equals 1, and this gives me the correct thing. So we get phi 1. Right. And now, you know, if I do this second row times this column, I'm going to get that 0. And what about the first row? If I multiply this, my RS, with this choice of R and S, do I get 0? And I do, because phi is a solution to this equation. So if you plug in phi here and 1 here, and then multiply this first row by that column, you will get 0 because phi is a solution to this equation. Now I'm going to subtract the other one, the phi bar. And I want to put in some R and S here and get a 0, 0. I want R and S not to be 0. At least one of them has to be non-zero. So I want R to be, let's say, phi bar, and then S equals 1, and then I get phi bar 1. Okay, so these are my columns. So this process, so I'll say what this is. So you have no idea why I did what I just did, but I'm going to tell you what I just did, is these two numbers. These are my eigenvalues, and for each eigenvalue I found an associated eigenvector. Okay. So now I'm going to find my matrix T. This eigenvector will be the first column. This eigenvector will be the second column. So there's the matrix T that I want. My diagonal matrix is going to be, so the diagonal matrix, so I'm trying to take this 1, 1, 0, 1 and write it like this, and I already found T. I found my T. Now I need to know the A and the B. Oh, that's what these are. This one's going to be the A, and this is going to be the B. So I'm going to have phi 0, 0, phi bar. So T inverse, I need to know T inverse. We know how to invert a 2 by 2 matrix, so I'm going to compute the determinant, phi minus phi bar. Over that, I'm going to take the, so I take the determinant, so phi times 1 minus phi bar times 1 is phi times phi bar. I divide by that. That's not 0, and in fact it's square root of 5. And then I do the phi and the 1. I'm going to switch, so I'm going to go 1 into phi, and then I get a minus on these two terms. And so I just inverted a 2 by 2 matrix here. And I'll go ahead and say 1 over square root of 5, 1 negative phi bar, negative 1 phi. And I know that this is square root of 5 because I computed it here. This one minus this one, the 1/2s cancel. Square root of 5 over 2 minus the negative square root of 5 over 2 gives me a square root of 5. So now I have T then I have phi 0, 0, phi bar, and T inverse. So T inverse, this is where this 1 over square root of 5 came from, but I'm going to write it out front. So 1 negative phi bar, negative 1 phi. So now I've done it. I've decomposed this 1, 1, 1, 0 matrix this way, and you can multiply this out and confirm that this is 1, 1, 1, 0. Now what I'd really like to do is say a to the power p is 1 over square root of 5 phi bar 1, 1 phi to the power p 0, 0 phi bar to the power p 1 minus phi bar negative 1 phi. So here I have a in this form, and I can raise a to the power p by just taking these diagonal elements, raising them to the power p, and that's what I did here. Phi became phi to the p, phi bar became phi bar to the p. Nothing else changed. And as you recall earlier, the pth Fibonacci number, so I'm going to be a little bit careful here. Some people start with Fibonacci numbers F0, F1, F2. Some people start F1, F2, F3. So depending on if people start with the index 0 or not, it may get slightly different looking answers to what you could find if you search on the internet, but it's not different. It just looks different. Oops, I missed that part here. FP equals 0, 1. Times and now I'm going to initialize. I would say 1, 1. So let me go back. So remember, if I said F1, F0, and then I multiply by this matrix 1, 1, 1, 0, it shifts. I get F2, F1. Multiply again, I get F3, F2, etc. If I multiply it to the power P, I'm going to get Fp plus 1 Fp, and this is my matrix A to the power P. And now if I take this and multiply it by 0, 1, so all I really care about is one of these two numbers. So I'm going to multiply this by 0, 1. That's going to be 0 times Fp plus 1 plus 1 times Fp. I'm just going to get Fp. Okay. So 0, 1 times A to the P times, well, F1 is 1 and F0 is also 1. This is Fp. Technically, it's the 1 by 1 matrix that has only one number in it, and that one number is Fp, but that distinction is not important. And so now, this is what we're doing here. I have the 0, 1, I have the 1, 1, and all of the rest of this is A to the power P. Okay, so, let's see if this goes somewhere. So I'm going to have 1 over the square root of 5 times 0, 1 times phi bar 1, 1 phi to the power P 0, 0 phi bar to the power P 1 minus not 1 minus negative phi bar negative 1 phi times 1, 1. Okay. So this is 1 over the square root of 5. So I'm going to do this multiplication here. I get 0 times phi plus 1 times 1. I get 0 times phi bar 1 times 1. I'm going to do this multiplication over here. I get 1 times 1 plus negative phi bar times 1. So I get 1 minus phi bar. Negative 1 times 1 plus 1 times phi times 1, I get negative 1 plus phi. So we do 1, 1 times, so I get times this first column, I get 1 times phi to the p plus 1 times 0. So you just phi to the p. And this is not centered. 1 times 0, 1 times phi bar to the p. Okay, so that's this matrix times this matrix gives me this one, and now I have this 1 minus phi bar, negative 1 plus phi. Okay, so I'm going to get phi to the p times 1. Careful. This is a 1 row matrix. This is a 1 column matrix. So I'm doing phi to the p times this first entry, which get phi to the p, 1 minus phi bar, and then negative plus phi bar to the p, negative 1 plus phi. So now, I'm going to recall phi is 1 plus the square root of 5 over 2, the power p. So this is phi to the p, and then I want to be careful. This is a lot of work to mess up now. So phi bar is 1 minus the square root of 5 over 2. 1 minus phi bar is 1 minus the square root of 5 over 2, which is distribute the minus, I get a minus plus. Okay. So we get the square root of 5 over 2 minus 1/2, I'm sorry, plus 1/2, which is positive phi. So 1 minus phi here is phi. So this is phi, so I get phi to the p plus 1 here. I get plus phi bar, 1 minus the square root of 5 over 2, the power p. And now let's check again. Oops. Use that for something else. Phi equals 1 plus square root of 5 over 2. So phi bar equals phi minus 1 equals negative 1 plus square root of 5 over 2, which is negative 1 times 1 minus square root of 5 over 2, which is negative phi bar. Okay. So this phi minus 1 here becomes negative phi bar, so I get phi bar to the power p times negative phi bar, so I get minus and plus 1 here. The formula for pth Fibonacci number, and here it's like I don't have to compute any other previous Fibonacci numbers. Okay. This is called, I believe, Benet's formula. To me, this is a beautiful application of linear algebra. So, again, recommending Math 222. Math 222 might seem like a lot of matrix multiplication that we did was not fun. It's just a lot of grinding through doing multiplications and additions, but linear algebra really has some beautiful underlying theory and some really interesting applications. So here we have a bunch of unnecessary stuff on the Fibonacci numbers.